In this video, I'm going to show a few ideas related to microsound, the granular synthesis, granulating buffers, synthetic grains, and constructing waveforms as well. Some things we did not manage to do in our class or cover in detail, so I thought it would be good to recap a bit with a video. What I'm going to start with is are synthetic granular sounds. And I'm going to start actually with a basic sine wave, which I'm not going to type in. I will give you have access also to the code material. So I'm just going to paste in here a synth def called SG or sine grain that has an envelope generator that will have an envelope that starts from 0, peaks to the maximum amplitude over a half a duration, where the duration is the input parameter. So sort of peaks in the middle. The sound is a sine wave where the amplitude is controlled by this envelope. The sine wave is then being panned, and this gets sent to an offset out, where the offset out is adding a bit more precision in terms of timing when we are organizing lots of grains. I'm going to start my server. And what I want to do after having added the synth dev is to sequence it or play many of these synths with some mechanism. I'm going to choose a routine. Let's say routine.play, and how many of those I want to play. I want to play lots of them, and I have not quite decided how many yet, so I'm going to say infinite 2, and I'm going to play my synth. And basically, I think most of the parameters I would like to just choose randomly and see where that takes me. I'm going to start with the frequency, which will be around random range, so from, I don't know, 100 to 4,000 or so. I'm going to make another one for the amplitude. Maybe we can just keep that constant for now. We want to also make the panning, so I'll make another one here that will choose a random panning. As you remember, panning goes from -1 to 1. And after having done the panning, I want to also get the duration, and I have a duration here that will be, let's say, 0.002. I think that's quite fine, or 0.005. Let's just after that in the middle, so to speak. I'm then going to make the synth def, and I'll add the parameters by saying the duration, frequency, goes the frequency, the panning, has the panning, and so on. And important with the routine and infinite 2 is to somehow wait, so I'm going to say duration.wait, and I'll try this. Some semicolons. Okay, not bad. We have a bunch of sine waves here behaving somehow, but I think the duration is still a little bit high, so I'm going to multiply this with around from, I don't know, 0.1 to 0.5, 10% of 5% of this, giving me also an overlap, because I was waiting for actually the same amount of time that the envelope here would take, meaning there will be no overlap. An overlap turns out to be a quite important parameter when we're working with granular synthesis. So let's listen again. And let's take it down. So one other interesting thing can be to, now we let's say have a sort of granular cloud, is to play with the envelope effects of each grain individually. Now if I look at the envelope a little bit outside, let's say it goes from 0 to 1 and 0 again, that's for simplification, and it would be something like this, and I can plot this. This would be my grain somehow. What would be nice is to use either a curve or our array of curvatures to sort of determine this. What I want to do is do something like 2 for the upper one and -2 for the lower one, meaning it goes like this. Gets a bit of a more exponential shape. How would it look if we would apply 2 in both? Get something like this. And I want to take that a bit more to the extremes by having it with a very sharp peak in the middle. So I'm going to add that to the synth dev with a 8 and a -8. And once I'm done with that, I'm going to play it again. We could play around with these maybe in the opposite way as well, to get quite distinct characteristics. Maybe I keep it at 4. Okay, what else could we do? We could say, actually, what would be nice is that some of these are changing in time, for example, the frequency range. So I'm going to do another thing, which is an envelope here, just like the one that I was doing. And I'm going to say this envelope will be starting from 100, which is the lower range, maybe goes up to 8,000 and then drops to 100 again. And I want to say how much that is. I'm going to choose 500 grains up and 500 grains down. It could be something to play with as well. And then I would like to index this, so there it will actually be like a range or boundaries changing, or something towards a tendency mask, but with the upper range changing only here. So I'm going to use the envelope, but I need to index it. And how can I index it? I need to know where in the envelope I am, and the only way to do that in a loop is to count how many steps of the loop you've done, or use the index, the loop index, which we can use here, or just use it, call it y, as is often the tradition. And I'm going to use y, and to make sure that we actually don't just read the upper limit, because what this could do if I would use the index in such a way, the random range would start from 100 to 100, go up to 8,000 and then 100 again, and would just stay there. So I need to make sure that after it reaches 100, it will loop the envelope. And I can do that easily by using the modulo operator, and I say 1001. Why is it 1001? Because the position 1000 in the envelope is the last item in the envelope. So when it reaches 1001, this will be 0 again. So it starts to recount from the modulo. You can easily also take the envelope out and verify all this. And that's about it, I think. I'm going to run this. And as you see, it loops it. Okay, what can we do more to spice up this small Microsound movement? One thing we could do, instead of having each grain sine wave, we could try to have it as a FM synth. So I'm going to say, I'm going to use here the PM mask. I'm going to say we have the carrier frequency, the modular modulation frequency is I'm just going to use the carrier frequency and multiply it by 2, and then the index I'm going to put something like an index 2, and maybe we could even have the index as an input here to put off the FM, and create maybe another one for that, which would be something like the FM starting at 1, going to 10, and going maybe to 2 again, and we can copy this here to put the FM or index, and we say FM or put it higher. No, I just didn't add the synth. Make it go the other way around. And so on. So lots of fun to be made with this. Turns out actually that will bring me to the next example, that actually we have a built-in UGen that does granular FM for us. It's Grain FM, which I'm going to mention briefly here, which is quite nice. Grain FM, where we can specify this. We need to specify a trigger like we do with T-grains and grain buff, which is how often we would like to have new grains. I'm going to make that be dust, so we get a bit of randomness in when we get new grains. So var dust is a trigger. I'm going to say the duration of each grain. Let's put it at the lower threshold. We enjoy low grain durations, get gritty sounds. I'm going to put a carrier frequency and a modular frequency higher, like in the previous example. And then is the FM index, and just for this demonstration purpose, I'm going to use a line that goes from something low and ends in something higher, and we need to say how long that takes, 5 seconds or so. And I guess that's it for the grain buff. Take maybe the volume down a bit. And we could build up from there by changing these parameters here, or having, as is often the sort of case with granular synthesis and granular textures and granular clouds, that we want to have many of them. So I'm going to improve my patch by using a mix.fill. I'm going to say I will have 5 layers of this granulation, granular FM, and inside of this fill I'm going to put some randomness. So the frequency will be around, let's say, from 100 to 6,000 to get a bit of a range, and I do the same for the mod frequency. I create a variable for the mod frequency, maybe something, well, it's fine to have it the same. I will do this, and I will say the frequency is random, the mod frequency is random, volume and the length of each grain. Close this. And we start to get quite nice grain FM sounds. But try higher density. And of course you could do the envelopes like we did in the previous example. I'm not going to do that though. I want to think about that. Besides doing this, we could also transform them, and I want to use wave shaping that I think could be interesting in this case. It will sort of distort the sound and produce sort of electronic sidebands. I'll explain it a bit in a moment. I'm going to use the fold 2, and instead of putting a fixed number for the folds, I'm going to use a sine wave that will be on the frequency of 20, and I take this bit, I think it goes a bit higher in volume, so I take it down again. So it gives a bit of a interesting sort of electronic sound and punchy sound, and not unrelated to ring modulation, but it's like, I think, more digital flavor. What is this fold 2 that I'm using here? So I think the best is to explain it is by plotting it. And we saw this also with in the class with binary operations. But I'm not sure I plotted it then. So if we use fold 2, it will basically be working like, yeah, sort of a distortion synthesis where we clip the input amplitude when it exceeds a threshold, and we can input the threshold. So what does happen is that the peaks get cut off, which is similar to clipping or digital clipping. However, here in wavefolding, the sort of amplitude peaks get inverted into a series of folds. And what are the series of folds? Let me check that. We can check that. If I put the threshold at 0.1 and I plot this, you see that actually, or let me go to 0.9. Start with 0.9. We see that instead of getting a smooth sine wave, when it reaches here 0.9, it will fold back in. Create one fold here. Now if we go to 0.6, what happens? We get larger folds. It goes to 0.6 and it folds this in until it goes here up again. Okay, and if we go even more down, we get even more folds. Bigger folds will start to seriously influence the wave shape, and this being a wave shaping technique, the folding. What is super interesting, what I'm doing here, is to actually not put a fixed threshold, which will give us a very audible result that might overshadow the sort of dynamics of the input sound, but rather to have something that's changing in time, which I'm using here with the sine wave, giving us this sort of lower buzz. So we can just do that with fold 2. There is also fold, but what I also want to show is that we have we could do this folding, and yeah, in the granular context, which was my original purpose, is to show that we could use folding with the grain FM, works interestingly together, and we could also, in the previous synthetic example, use fold or other wave shaping methods to sort of transform each grain individually. I'll leave that out though now. I just want to show that what we can also do is to use fold.ar, and fold.ar will give us we can control both, so we can put input sound and the lower and the higher thresholds. Okay. Whereas with fold 2 there is just one threshold, but here we have a lower and higher, or different inputs for those, different controls over those. So I'm going to take advantage of that, and I'm going to use just try a sound example with fold.ar, and I'm going to use not a sine wave. I'm going to use the sine wave of the feedback, which can always add a bit of interesting overtones in cases like this when we're processing sounds. I'm going to put low frequencies, bit slightly different in the left and right channels, and then I can choose the feedback for the Synosc feedback. I'm going to modulate that parameter with the LF noise 1, giving me ramp noise. I'm going to have a low frequency for that, 3 Hz, and put the range of the feedback from 0.1 to 2 or something would be nice, I think. 1.8 would be nice. Something like this. Now, that will be my source. I am then going to think how I can compose for the low and high thresholds of the flow of the fold. I'm going to continue with LF noise, but LF noise 2 in this case. It gives a quadratic noise. I put it on 4 Hz, also low frequency, and I will the range needs to be somewhere between 0 and 1, or minus 1 and 1, and I'm going to put 0.1 and 0.5. And the higher one, I'm going to put a sine wave. Can also be good to blend these with regularities and irregularities, and the sine wave here produce regularities. I'm going to have slightly different for the left and right channels, and make it go from 0.5, but exceed the range, so it gets a bit clipped, low and high. So a little bit of let's say extended example, but the idea here being that we can be quite creative with the wave shaping, not always considered as a Microsound technique, but also in the context of processing both Microsound and here the sine wave, feedback sine wave. Going to be sure it's not too loud, and that's it. We could play around with some of these to get different ones. And the fold adds an interesting sort of temporal quality to it. So the next thing we want to do is actually do granulation with buffers, but not like we did in class, where we would take a sample and put it into T grains or grain buff and granulate that, but to have a living buffer where we can actually fill it with whatever it is we would like to granulate, and granulate from that in real time. And by doing that, I am actually going to start by allocating a buffer, which we will then be using to fill up with input sounds, and then granulating those input sounds. So what I do, I would say B is buffer, but not read, rather allocate. And I put the server, and I need to say how long I would like the buffer to be. I'm going, how many frames would that be? Would that be then the sample rate of the server multiplied with how long I would like? So if it's 5 seconds, I would say it's 5 seconds or 3 seconds. And then we have a buffer. So what am I going to do? I'm going to granulate something, write it to a buffer. No, I'm going to have some source. I'm going to write that source to a buffer, and then I'm going to granulate that buffer. It's actually 3 different tasks, and I would like to write 3 different synth devs for that. Make another section here at the top, synth devs, and the synth dev, I'm going to make the first one, it's called source. The source is going to be just whatever I would like to be writing into the buffer. I'm going to have then something called a writer, and the writer writes to the buffer, and I'm going to have something called reader, and the reader reads from the buffer, and they're just empty for the moment. What should I use as source? So I'm actually going to be using, I will actually just try to use a sample to start with. Why is that? Is because this we have this vocal sample. It's nice to play the vocal sample to hear discontinuities and so on. Then we will swap it to something maybe more interesting later. So I say buffer.read as, and I put here this, and I'm going to read this. And maybe we could even, well, let's work with that. I have the source, the writer, and the reader. Let's start with the source. That should be rather simple. I'll have arguments, which is the input, so where it should read from. Where it should read from, is that really necessary? Well, it's this maybe let's call it sample. Which sample it should play? That should be 0. Which output it should be writing to is 0. And then I make a variable, which is the signal, the sound signal. I'll be using just the play buff, and the play buff will be playing one channel mono sound. It will be playing the sample, and all the other arguments I'm just going to leave it default, except the loop. I'm going to use loop as one. A nice one. We'll be testing this out. I use out.ar, and so that the source will write to this output bus, and what will it write? It will write the signal. Et voila, this is it for my source. Now, the second phase is I'm going to take the source, and I'm going to be writing it to a memory buffer, and that memory buffer is here already allocated. So this is a writer, and the key ingredient here is to use buff writer. And buff writer will tell us that we need to write something to a buffer, some buffer, and we need to control the phase, so it goes from what is the phase? Let's look at that. You can see with the buff writer is the phase is the index into the buffer, so where in the buffer it's writing the input. Okay, so let's start with the in. What should the writer be writing in? I'm going to say the signal is the input signal. It will use in AR. Which bus? Well, that should be the input bus, right? I say in. How many channels is 1, and which is already default. That's it. We're missing here the argument. That's in. Give it a default value. And then we have the input being put into the signal. So dear buff writer, we give you here the input. Next thing is the buffer that we are writing into. Well, we're not going to be doing much with it. We just need the number. And then we here say buff, we put it to 0. It's this buffer here, which is actually number 6 at the moment. but the default value can be 0. We'll be hot swapping that later on. So then we have the buffer, we have the signal, we know where to write it to, and then we need just to have a sort of running phase that tells us where in the buffer the signal should be written to. How can we do that? We saw just previously we could use line. We know line. We could use rampable things, but a very convenient one is to use the phasor, because it will reset. It will make a ramp up and will reset itself. I'm going to call the variable position because it's saying the position of where in the buffer we're going to be writing. I'm going to say a phasor, and the phasor we're not going to be ignoring this trigger behavior. We're going to be using just the rate at 1. It will be starting in 0. It will always be starting in 0. The buffer go to the end of the buffer. How do we get the end of the buffer? We just say it's in frames, so it's buff frames, and that is the buffer. And this buffer is an empty memory buffer that we are just using for granular purposes. Okay, and then we have the buff writer, the signal, and the buffer, and the phase. Now, there's one important concern which makes this whole game a little bit complicated, and that is that the buffer, which is here 3 seconds, or we can choose how long it is, it will be filling up until 3 seconds, after which it will then be overwriting itself. So a key behavior needs to be that the granulating synth def or synth defs will not be touching on sort of the contact points of the buffer where it's actually writing to. So we can make it go a little bit later. It needs to go a little bit later, the granulation process, than the writing process. That's relatively easy, but it means that the reader needs to know where the writer is in order to be a little bit behind. So how I'm going to address this is that in the writer I'm actually going to also output the position where the phasor is. And I'm going to give a new input for that, out 0. Out AR, and that goes to out, and that goes to position. The position of where we are actually writing to is going to the output. We're not going to be hearing it, but we're going to be using it. Okay, then we have 2 of the 3 steps done. We have the source, we have the writer that writes into a buffer, and we have the reader, and the reader is... no, we don't have the reader. We're going to have the reader now. Let's see if there's any typos or so. Let's hope this is all good. And let's proceed to the reader. So, the reader, the key ingredient in the reader is the granular Eugen. We can use T grains. We saw that quite extensively in class. A very related one is grain buff. We also saw that one. I'm going to use grain buff for this. What it says number of channels, which is going to be just 1. We're going to stay with the mono one for now. We need a trigger, something that triggers it, just like we had with the grain FM. When do we want a new grain? Good default value for those, just like we did with the grain FM, is about 20 times. What should be the duration? I'm going to choose something like 0.4 is a nice duration, which is the buffer. Now we start to need some inputs. I say argument is buffer, and the buffer is 0, although it won't be 0. That's the buffer. The next thing is the rate, which is the playback rate. I'm just going to keep it at 1. And now comes the position. So where in this buffer here should we be reading from or granulating from? And that is something I need to have as an input again. And I'm going to have an input here, which is the position. Or the input, yeah, we can say the input of the reader. The reader has an input, and I'll make a variable position, and the position will be reading in.ar from this bus number, which is in, and then here we have the position, or 2e, so that would be position, and the rest we are just going to ignore for now. Now, actually, so the grain buff expects something that goes from 0 to 1, whereas the phaser was going to 0 to the end of the buff frames, which is something much bigger than 1, right? So the position, we will have to scale it, and we're going to say position is position divided with buff frames of that buffer that we're using, and not post but pause, and then we're about good to go, except we still missed to say out AR, and I'm going to say it goes to output bus 0, and this is the signal. We need to declare that variable signal. Let's put it in more lines to keep things a bit more clean. And signal is like this. What goes to out? We could give some value to out if we need to process the reader. I'm just going to send it to my sound cards left and right, so starting at 0, and that will be the signal. And maybe we can just multi-channel expand so that it goes into the left and right channel, and work a little bit more with that later. So one last thing is, and this can actually be quite complicated, let me add them before, is the thing that I'm going to be taking the source, and in the writer I'm going to be writing it to the buffer in the memory, and then I'm going to have a reader that's going to be reading this and granulating it. Now, what happens if the for example, the granular reader has a large grain size, and the writer is very busy writing in memory at the same time? Couldn't it happen that the reader actually exceeds the writer and starts to read from a buffer where there's nothing into it? Doesn't the reader have to be a little bit behind so we are sure that there's actually audio in the buffer that we're supposed to granulate? So yes, and we can think about many ways to do this. For example, to calculate, which is the duration of the grains and make sure that we don't exceed that, or so on. I'm going to start with something simple, which is just to have a little bit of delay, and it goes from 0 to 1. So I will start by having this by just giving a delay that will be 10% of the duration of the buffer. Alright, and then I'm going to wrap the position. Why? Because in the beginning it will be 0, so I need to wrap it so it falls within the range of 0 to 1, 0 to 1. So we can always pull this, might be nice in the beginning. See also what's going on, because it's the key ingredient here is where is the position of the phaser. The phasor of the writer goes to the out, and it's used again in the reader. And here we put a small delay, so it lags a little. The reader lags behind, trying to. We're not completely sure of it, but trying to increase the chances that we are actually that the buffer that we're granulating contains audio. All right, so I have this, and then I have the buffers as well. And what I'm going to do now is to make sure that these things connect together. And to do that, I'm actually going to make some buses. I'll just do them here so I don't do it again. I'm going to do one for the source. Source bus. And I'm going to have another one for the writer. Okay. I'm just going to keep them like this. And then I need to do, how I'm going to do this, I'm going to start with the source. And the source will be playing what? This buffer here, C. Okay, so we hear C.
Alors, Jean, un glas tiré.
You know the sound quite well. And the source will be reading this. So that is the sample. And the sample will be then C. You can say C or C.buffnum. Okay. What is missing from the source is the output. So the output where it's going to be writing the sound to, and for this I have created the source bus. So this is the source, and the source has the output as source bus, and the sample as bus number. That's it. So after the source comes the writer. And the writer and if it comes after, well, the order, if we're not explicitly setting the order is a bit top to bottom, so you first start the last thing and last the first thing, in this order of events. So we start the source, no, we end by the source. We start with the reader, then with the writer, and then with the source, because the source is the first thing. That's how we need to set it up if we just respect the default order of events in SuperCollider. I'm going to say the writer should write into a buffer, which is the buffer that's the allocated one here, B. I'll keep allocating this again and again while we are developing. That's the buffer. What was more with the writer? So it needs to, the writer needs to have the in and the buffer and the out. Okay, the in, what was the in? The in of the writer was the source bus, which is the out of the source. The buffer is the buffer B that we are granulating. And then the out, what's the out of the writer? The out is actually the phasor that we're going to be using in the reader. So that would be the writer bus. So in is source bus, out is writer bus, and the buff is B. Okay. Then finally we're going to have the synth reader, and that reader is going to be having also some things to do. So it's going to be reading from the buffer B, it's our granulating buffer. It's going to have an input, which is actually the phaser, nothing to do with the sound, but only the position of where it should be granulating about. Remember the thing we delayed a little bit. And so the buffer, the in, and then I guess that's it. I hard-coded the out. So for the moment, that should be it. Let me verify this all again. So reader and then in. Yes, I think that should be it. So let's add the syntax again, load the buffers, and run the patch.
Alors Jean, un glas tiré, où, oh, l'urne gourant le si guignard. Alors,
okay, so maybe it was a little bit loud here. Just take that down. What am I tracing? I'm tracing the position. So of interest here is to look at where does it start. It starts at -0.1. So what we will see here in the post window is we start from 0.9, but only when we reach 1 and we actually loop back to 0, then we have sound in the buffer. So that's why the first 10% will be silent.
alors Jean.
No, it's not, because there's something in it. And I run it again.
Alors Jean, un glas.
So here in the beginning, nothing. And then as we reach this one, the writer that has been just a little bit ahead, so we missed this in the beginning. Maybe we can make it even more prominent.
Alors,
only when we reached the beginning, then we heard sound. It doesn't mean that the sound was not written, because just from the beginning, the writer started to write in the beginning position of the buffer. It's just that the reader is a little bit behind, lagging a little bit behind. And there's a more sophisticated way to calculate this delay of how we need to be behind, but I think just keeping it a little bit behind is good enough for our purposes here. So what we have now is a source, a writer, and a reader. Basically, we can reconstruct the sound. Well, it sounds exactly the same, but it's going through this buffer. So let us take this example. We can have a different thing. We can put like lower granular rate.
Alors Jean, un glas tiré,
or play around with the position and things like this. Okay, my purpose with using the voice was not that I wanted to get into granulating the voice. Rather, I was thinking this would be a good starting point to just hear, and we even hear that it looped here, that we can have this sample and it looped. We can even, now it's a 3-second buffer. The voice is even longer. It's 11 seconds, but we see that it doesn't matter. The thing loops, the voices loop, the loop are not in the same rates, but the whole thing works together. Source, writer, and reader. All right. I want to change it and granulate something different. So I'm going to remove this C buffer here. I'm gonna, no, not in this one. In the source, remove this sample thing. And I'm going to put something different in the source. I'm going to put the signals, but I'm going to put something like the GenD. granulate the GND. Why shouldn't we do that? I'm just gonna use the default arguments, but it's quite loud, so I take it down in the volume. I have the writer, and then with the reader I think we can do lots of things that would be interesting to do to granulate it. So what I would like to do is to play around with the position. Maybe I'm going to remove this, the wrapping functionality, and put it here. So position equals position wrap. We don't need to pull it anymore. We knew it was working. I'm going to say position. I'm going to modulate the position, so to speak. Position is position multiplied with LF noise 1. Put the LF noise 1. Put it at 10 hertz, and just a little bit around the place where it could be playing. I'm going to take also the rate. So the rate, maybe an argument for the rate is 1, and I'm going to override it here with saying rate is LFD. So the dynamic noise, where it recovers faster, can have a nice variant of LF noise 2, the dynamic cubic noise. I'm going to use the dynamic cubic noise, LFD noise 3. Bit of a lowish frequency, 10, and say, well, it would be range, but would be around the rate. So if we say rate is 1, I'm going to say rate times 0.5 and rate times 2. That would be the rate here, and I'm to use this rate instead, and the position. So then the reader, I can just use the default values. Try this, and did I forget something? Yeah, this was not needed because I have this already. Missing a few things. I'm going to be using GenD3. And there's a typo here, range. And we run it. Actually, we heard that the buffer was there was still voice in the buffer, which is a bit annoying. So I'm going to just combine this code. So we put here fork, and we'll put this here. So I don't need to run anything multiple times. So first add the synth defs, then the buses, then I locate the buffer, and I call s.sync, and I run this. This delay is a bit too much. And so I start to granulate the GenD. Let's maybe have a high rate of things. What could we do more? We could have also do many things that we mentioned also in class and so on. The other examples that we with for example coupling parameters or processing them in different ways, going slower through the buffer, things like this. Or we could also have many readers at the same time. So I'm going to do that. I'm going to do a loop. I'm going to say I actually want to have 8 readers. 8 readers of, I'm going to be using the index to read the buffer, where they all have slightly different parameters. Let's type it like this. I'm going to think what could be 1. Well, the rate is 1 because yeah, I could put a random number for the rate, something like goes very down, very low, so the pitches would be, we have a broader range. Another one which is always very nice with granular synthesis to manipulate is the duration. And I'm going to be using the duration plus 1, which is the index, so that we have actually layers with very low grain duration and layers with high. So I plus 1 times 0.01, and I still need to add that then, duration for to the reader, and I think that should be more or less it. Maybe need a semicolon here, make this a bit more compact. So something, let me take this down here. Well, whatever, let's just keep ours or frequency 100, play with the Gendi a bit. And so we have 8 readers of the Gendi being granulated with the rate, with the position and the rate are being modulated, and yeah, I leave the other parameters for you. And this was my granulating a buffer example. Alright, I think that's it. I will remove this. You can access the code from the link and read it there. What we saw here, well, it's kind of funny I chose the Gendi, was a bit arbitrary, but what we saw here, we could be having lots of small grains and lots of low durations to get more kind of gritty sounds and compose there. And I guess an obvious next step, or maybe rather next jump, is to try to find ways to actually compose or create the waveform itself. What I want to do here is start by making a regular waveform shape, and then see how we can find ways to variate waveform shape to get to this kind of thresholds of microsound and that we have discussed in class. I'm going to choose as beginning a triangle wave. We did in class a bit the saw wave, so maybe we try a bit something different. So I'm going to choose the triangle wave, and would think I want to start with a pattern. How could I, because we know the pattern so well, how could I make a triangle wave? Well, I could make a P sequence of two series. So how are the series? We know the series, and P series when we will start somewhere, and if I would like a triangle wave that starts from -1 and goes to 1, well, I would go up and up by 1, or whatever. We could choose other numbers, but this is our point of departure, and I could say as stream and get the next 20 values here to plot them, and it goes up from -1 to 1. How would I go down again? Well, I could say I want to go up, but -1, right? So I go down again, and to make this go in parallel, no, in sequence, I'm sorry, I can make a P sequence that has the series that go up and down, and I can just take this here away and put it here. And what do I get then? Is to say next and 40, something that starts in the down and goes to 1 and goes down again. Well, that would be nice. So what I'm going to attempt is to try to do this in audio. And by doing this in audio, I'm just going to use here the curly brackets dot play, as we often do, and I'm going to take all this. We all have it on the P sequence here, but I'm going to swap the P's for the D's, because we're going to be using the demand rate. So I have a D sequence, a D series, followed by another D series, and one thing I didn't do here was the repetition, which I will have as infinite. Okay, that's the sequence. I'm going to connect that with a demand AR, and I'm going to be putting that, I have to trigger that, so I'm going to say impulse.ar. How often should that trigger? I don't know. Let's start with our famous 20. And the reset, we'll ignore that. And then the demand, and that will be this here. We need to put it in a variable. Let's call it try for the triangle. And then we have the triangle. And we take it a bit down the level. And that's about it. Let's take the frequency a bit up. Well, we definitely have a periodic sound. But let's see what's going on. But it doesn't progress smoothly between the steps, but rather in the steps themselves, making this kind of step wave, triangle wave, which actually sounds more or less something like a square wave or so. But we're getting there. But what we are seeing is that we can easily use the demand patterns, so demand rate things, to help us create waveforms. So I'm going to hold that up with the triangle. We could do that. We were going to attempt to construct a beautiful triangle wave, but we can also play with this model as it is now, with sort of thinking that we haven't learned to use and love through working with patterns. So I'm just going to copy this and think, well, how can I actually maybe vary this? And say it will go up, but I'm going to make it maybe exceed the limit, and I'm actually going to make this a random thing like a d white. Doesn't have to exceed, I can just go 1 to 20, 50 and just take this a bit more down. And another one here. So this will mean how many of those, so the series will be longer, but they will be different every time. I'm going to be using this, and I'm going to try to iterate that at a much higher frequency and just expanding that stereo so we get actually a little bit different. Or we could expand it, the stereo expansion here, so that the D whites will actually be a little bit different each time, giving us sort of a stereo waveform. And yeah, this is how it plots. Looks quite nice. Let's listen to it. So we do hear some of the fundamentals. We do have pitches here, but what we hear a lot is the discontinuities when actually it is going above and then it falls back to the downwards motion. When the upwards and downwards motion don't meet, makes a click, and that click becomes very prominent. Although listening to it at this can not be bad as audio material per se. Which wasn't our goal, so I'm going to abandon that and continue. And actually use the infamous demand and fusion. And the demand and fusion will actually help us to interpolate between points. What am I going to do? I'm going to just say the demand and gen. That's an AR, and we should have levels and durations. Well, the levels we already had here. Just to take these levels. That was just a pattern to make our triangle wave. And I need to make this. That's the levels. And what I would like to do with the duration of each of these steps is just to use the duration of an individual sample. I'm going to expand this and a bit lower so it doesn't reach the full amplitude, and we should hear it. And we get a beautiful 1K triangle wave. So I guess in that sense our goals are now met. We have the series that starts from -1, goes up, and then another goes down. And because we're using the demand and gen, the values are interpolated. It makes these breakpoints and interpolates between them. And then we can say the duration, so how often that is. What becomes then very interesting is to think about how we can sort of vary this. For example, I want to say I want to have this D series, okay, but I would like to actually synthesize, compose a little bit how the duration of each of those. So I'm going to say the sample duration will be a D sequence. I'm going to make a D sequence, and the D sequence will contain actually 2 random generators, one from 1 to 10. I'm going to have just 4 of those, just arbitrary, whatever, and then maybe 10 of another one, which have a wider range. Or 4 again is fine. And I'm going to loop that infinitely. By doing so, or 10 or 20. We get a sort of a waveform that is sort of varying from within, we could say, opening for lots of usage with patterns for composing it, both the levels and the durations. So another example could be to parameterize that and play around maybe also with processing that. And I use here a demand env gen. I'm going to actually make here this to make it play curly brackets, and I'm going to say, okay, demand env ugen. I'm going to put parameters. What could be the parameters? They could be the minimum value, but just say the minimum value would be -1. Maximum value would be, I don't know, 0.4, and the sample duration will be sample duration. I'm going to make a sequence for the levels and the durations of the sequence. That is a minimum negative, and I'm going to expand it in stereo. So it's very nice to work with multi-channel expansion with these waveforms, because they're slightly different in different speakers. Max negatives and max like this. And I need to say how I repeat them, and I will say infinite, and I'm going to use just the t white to say sample duration times 100 for the durations. Then I have this here, and I wanted to also transform that. So we saw fold. A very related one to fold is something that will not fold the segments back in, but wrap the segments back in. And I'm going to use that and use this sine wave to control the wrap and put that on a low frequency like 0, 0, 1. I multiply this with 0, 1, 1, or 0, 3 can be fine as well. And that's what I wanted to do. I need to close this. And then I basically have 2 points which could be parameterized, and then a randomness of the duration and the sequence of this. And the typos. So, where am I? Something wrong. Demand env gen is not taking an array. Why did I put that? Or put this. Yeah, maybe the wrapping isn't adding so much, but the key, what I'm trying to aim at here, is to use different patterns for the levels and durations, use parameters, and arrive at strategies to compose the waveform with these kind of gritty microsounds and noisy textures that can be offer a lot to explore. So that's it for today, or for this video. We've seen granulation, we've seen granular synthesis with synthetic grains and FM synthesis, and now with waveform, composing waveform with demand ugens and demand env gen. Good luck with that. Thank you.